Students, we were discussing that first of all we were discussing the phase of a wave. The phase of a wave we have already learned in the theory classes, and we have also seen that how does a phase changes with time. And now we have already come across that how does the phase changes with respect to position. Okay, so just repeating the last thing, that if you consider the two particles whose mean positions are at x and x plus del x, okay, that means if you consider this, yes, so the phase difference that you are able to see, that is del phi, between the two particles at any instant time t, can be obtained from your first equation. That means this equation. Okay, so I've written this equation that your del phi will be equals to minus 2 pi by lambda into del x. Now students, I will tell you that why I have written this negative sign here. So the negative sign indicates that for a wave traveling in the positive x direction, that means just imagine this is your graph. That means the wave is moving in this direction. This is your positive x axis, isn't it? Okay. That means here the wave is moving in like this way. Okay. So the that wave traveling in the positive x direction, particles having higher values of x lag behind in phase. Obviously, that the particles which are having higher values of x, they will lag behind in phase. Okay, so we can ignore this negative sign also, and we can write the phase difference between the 2 points. Okay, this we are writing it just from the graph. Okay, but if you want to ignore, then also you can do it. So by ignoring this sign, we can write that for any instant of time t, the phase difference between the 2 points that we have considered can be written as, I am writing a short phase difference between 2 points. Okay, students, don't consider it as potential difference. This is your phase difference, P dot small d. Clear? That is your 2 pi by lambda into path difference. Path difference between those 2 points. Okay. So, if your del x is your lambda, okay, that means this part. If your del x is your lambda, then the phase change is 2 pi. Okay, that means just place here lambda. So okay, since we are ignoring this sign, so we will get it as only lambda, isn't it? Sorry, 2 pi. Repeating once again, you are putting del x as your lambda. Okay, so what will be your phase changes? That means after ignoring the sign, you are putting del x as your lambda. So a lambda will cancel, and since you have ignored the sign, so your phase change will be equal to 2 pi, isn't it? So what your, yes, so what you can say, yes, phase changes equals to 2 pi. Okay, so what you can see that if the path difference between 2 points be one full wavelength, then the points are in the same phase with each other, isn't it? Path difference between whom? Between the 2 points in one complete full wavelength. Clear? So then the points are in the same phase with each other. Okay. Since we are considering that the path difference between 2 points in one complete full wavelength. Okay. Now this we have assumed in the first part. Now, if you assume your del x as, I am writing here, del x as your lambda by 2. Okay. So what will be the value of phase change? Again put it here. Okay. Or better in this formula also if you want. That means just after ignoring the sign, del x will be lambda by 2. So what will happen? Lambda will get cancelled, and 2 will also get cancelled. I'm considering this equation. Okay, so you will be left with only pi. So your phase difference, that means your del phi will be your pi. Okay, isn't it? So what you can conclude, that if the path difference between the 2 points be half the wavelength, okay, that means half the wavelength means lambda by 2, okay, then the points are in the opposite phase with each other, isn't it? Since you have considered your del x as your lambda by 2, previously what you had? Previously we had considered del x as your lambda. Why? Because you have considered the phase difference between 2 points in one complete full wavelength. Okay. So then the points are in the same phase with each other. That means we are talking about the previous equation. Now what you are having? That since you are getting del phi as your pi, so obviously from this point what you can guess, that the obviously the phase difference will be just the half of the wavelength. That means since you are getting as lambda by 2, and obviously since you are getting this pi, so the points will be in the opposite phase with each other, isn't it? From this pi only you can saying this, that the points will be in the opposite phase with each other. And in the case of the previous one, repeating once again for the last time, your del phi was your 2 pi. So obviously from this point you can see that your points will be in the same phase with each other. Is it clear? Okay. So I think we have discussed a lot regarding the phase changes, that how does the phase change with respect to time, this part, and how does the phase changes with respect to position. Clear? Now students, we will discuss one sum. Okay, so let's do that. Okay, and one more thing students, before doing the numericals, I will tell you that we have discussed many equations from the wave equation chapter, wave motion chapter. Okay, that means the equations for the displacements, how in what are the alternative forms of expressing the displacement of a particle. Okay, with so and so constants given. So you will be going through all those equations for your numericals, and also the relation between the particle velocity and the wave velocity. Each and every part students, I'm telling that you have to go through, especially the equations. Okay, before doing the numericals. Okay. Yes, and I also did the derivation. If you just go through the previous classes, if you just go through, all the derivations are also done so that you can understand easily. Okay, so let's do the sum students.